Okay, Lewis dot diagrams. These are diagrams that are going to be useful to us because they show us the structure, how things are bonded, where things are spaced when they are bonded. So, first of all, in order to do a Lewis diagram, you need to know how many valence electrons there are. So, in the case of lithium, lithium is an alkali metal, and by now you should know that alkali metals only have one valence electron. So, I would just put a dot. A dot represents a valence electron. One dot. That's it. Magnesium is an earth metal. It's got two valence electrons. So we'll put two dots. Aluminum has three valence electrons. And I'm going to put three dots, but I'm going to space them in a way that's based off their orbital diagram. So if you recall, aluminum is 3s2, 3p1. Okay, so see how there's four orbitals? If you imagine each orbital is a side around the letter, like this space here, this is the first orbital, this one. This space here would be this one. This space here would be this one, and this space here would be this one. So since it's only got three electrons, I'm putting a pair above, and then I'm putting the one here. Okay? So based on that logic, phosphorus has 5 valence electrons, and they're spaced like this. So when I place my electrons around phosphorus, we start with a pair on top, and then a single electron around each side. Fluorine. How many valence electrons in fluorine? 7. So since there's 7, 1, 2, 3, 4, 5, 6, 7. We have the one side that has only 1. And xenon is a noble gas. It's got 8 valence electrons. It's full. Okay, now again, Lewis diagrams are based on the octet rule. As you can see, right, we're only paying attention to the valence electrons. And yeah, so that'll come up again later. Okay, so that's for single elements. That's fine, but Lewis diagrams are not useful for single elements. They're useful for when the elements are bonded to each other. So there's a series of rules. I'm not going to just read them right now. I'm actually going to read them to you as I go through and do the samples. Okay, so let's start with the first sample here, hydrogen fluoride. I have 2 elements, and I'm just going to draw them next to each other. I'm going to leave a little space in between. Okay, so I'm going to the first rule. How can we draw these symmetrically? I just did. I just drew them next to each other. Okay, step 2. Count all the valence electrons. So let's count the valence electrons. So hydrogen has 1. Fluorine has 7. So we're looking at 8 total. Okay. Rule 3. Place pairs of electrons in each bond. So the bond, these 2 atoms are bonded this way. So a line constitutes one bond. It constitutes a pair of electrons. All right. Step 4. Complete the octets of the atoms attached to the central atom by adding electrons in pairs. Okay, so put a pair here, put a pair here, put a pair here. Place any remaining electrons on the central atom. I don't have any more remaining electrons. I've used up all the valence electrons that I had. So when you're done, you need to check. You need to check and make sure it has an octet. Does fluorine have 8 electrons around it? It does. It's got 6 lone pair electrons, but it also has the bond, and the bond is the last 2. So that's 8 electrons around fluorine. Hydrogen does not, because hydrogen is an exception. Hydrogen only has a 1s subshell. Right? Remember, a subshell of S is 2 electrons. So hydrogen is exempt from the octet rule. You don't have to worry about making sure that has 8 because it can't have 8. It can only have 2 electrons. Okay. Let's try the next one. Let's try water. Okay, so H2O. Well, let's put the H in the center because that looks symmetrical. Let's count up our valence electrons. You got hydrogen, which has 1 of them, but there's 2 hydrogens. Oxygen has 6, so again, this brings us to a total of 8 that have to be used. All right, so step 3, make bonds. There's a bond here and the bond here. Step 4, fill up the octets. Well, hydrogen can't have an octet, but oxygen can. And as of right now, I have used up my 8 valence electrons that I counted, and so I am done. Oxygen has 8 around it. The hydrogens don't need 8, so we're done. Okay, so these are like simplest scenario. Let's try the next one, carbon with bromine. Okay, valence electrons in carbon, 4. Bromine has 7, but there's 4 bromines. So 7 times 4 is 28, plus 4, that's 32. Now we have 32 valence electrons to use. It's more than the last ones, but doesn't make it any harder. Okay. Symmetrical arrangement. It would make sense to put carbon in the center, right? Bromine, 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 bromine. Next step, place your bonds. Okay, so how many electrons have I used in that diagram so far? 8. And I need to use 32 total. So we just start putting the pairs in. And what you should realize then from this shape of this diagram is that I will have 4 groups of 8, which is 32. So before you finish, ask yourself, does each atom have 8 electrons around it? Yes, they do. Even the middle, even carbon has 8. And I've used all 32, so I am done. Okay, let's try this next one here. CH2O. Do you guys know what this is? What this is a formula for? Seawater. This is C, and then the formula for water, seawater. All right, so let's count these. We got 4 from carbon, plus 2 hydrogens, plus oxygen, which has 6. All right, so we're looking at a total of 12. Okay, so interesting point that comes up. I said I wanted this symmetrical, but, and hydrogens, because the hydrogens can only have 1 pair attached to them, hydrogens can never be in the center. So now it comes down to which should be in the center, carbon or oxygen. And so if we were to go back and add one last rule, here, we'll call it rule 1B, is that the lowest electronegative element goes in the center. Okay? So if I know I have to put the lowest one, the lowest electronegativity in the center between carbon and oxygen, which one would that be? Carbon, yeah, carbon. All right, so let's put the carbon in the center. I've got an H, I've got an H, I've got an O. All right, now we start placing our bonds. Okay, so I've used 6 so far. I have a total of 12 I can use. If I put my pairs here like this on oxygen, we run into a little bit of a problem. That is not correct. And why is it not correct?
Carbon doesn't have an octet.
Yes, carbon does not have an octet. So, what could I do? The number of electrons that I have is what I have. I can't generate any more. So I have to make this work with 12 electrons, 12 valence electrons. So I'm going to erase a pair of dots on the oxygen. And instead of them being like a pair of electrons, I'm going to make them a bond. And that's what we call a double bond. The reason why we're double bonding is because now both carbon has an octet, but also oxygen has an octet. And by them sharing two pairs instead of one pair, we can make them both have an octet. And that's going to happen. That's going to happen every now and then. When you run out of electrons, you need to make a multiple bond. All right, let's add that to the rule as well. Oh, it's already a rule. Rule number 6. If the central atom does not have an octet, form double bonds or triple so that you have an octet. Okay? NCl3 5 for nitrogen. There's 3 chlorines. Each chlorine has 7. So 21 plus 5 will give us 26 total. So nitrogen in the center. There's 3 chlorines. It doesn't matter if you put them like the third chlorine on the top or bottom. Draw in your bonds. Fill in your octets. How many electrons have I used so far? I've used 24. I have to use the number of valence electrons that I counted. So the last pair goes on the center, and hopefully that fulfills the center's octet, which it does. All right, so I clearly have 3 atoms on the outside with 8. My central atom has 8. I've used all 26. We are done. That's the Lewis diagram. Right? So let's just do this one last example here. Sulfur has 6. Oxygen also has 6, but there's 3 of them. And if something's got a charge of -2, does that mean there's more electrons or fewer electrons? More. So we have to add 2 more electrons to that. Okay, so 3 times 6, 18, plus 6, 24, plus 2, 26. Yeah, Kristen.
What if the -2 charge would be on each individual oxygen and would be on
Ah, good question. So when you're counting up your valence electrons, think of them as like a community pot. They all put them into the same place, and then they're redistributed around however many atoms there are. So sulfur in the center, oxygen, 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 bond, bond, bond. And there we go. 3 groups of 8 and an extra lone pair, so that's a total of 26. Now, because this was an ion, right, whenever you have an ion that you're drawing, we call this a polyatomic ion, you have to put brackets around the structure with a charge in the corner to signify that it is an ion, just to make it stand out. How are we doing? Good? All right. All right. So we will do more Lewis diagram drawing next class. All right. Now we're going to transition because we need to start talking about today's lab. So let's stop recording this.